Hi, my name is Ching and welcome back to Data Structures in C++. In the previous lecture, we talked about priority queues and one way to implement them, with binary min heaps. Then we talked about how to use arrays to implement binary min heaps efficiently. Today we're going to talk about graphs and some variations, such as weighted graphs or directed graphs. Then we'll discuss how to represent graphs in computers. After that, we'll use examples to demonstrate how to traverse graphs. So graphs are just a collection of vertices and the edges that connect them. Here's an example of an undirected graph. As you can see, the edges are just lines which connect the vertices or points on the graph. But we don't need to connect all the vertices. Vertex 7 doesn't have an edge connecting it to other vertices. Or in other words, it doesn't have any neighbors. We can also have a directed graph. Here, each edge has a direction. For example, the edge from V3 to V5 is different from the edge from V5 to V3. Now that we know how a graph looks like, we can talk about some of the graph terminologies. As we saw from the last slide, each vertex may have a different number of neighbors, or more formally, adjacent vertices. We call this number the degree of a vertex. For example, the degree of A is 3 because its adjacent vertices are B, E, and D. But the degree of, let's say, G would be 0 because it's not connected to any other vertex in the graph. But you may ask, what about A and F? They're also connected through A, B, C, and F, just not a single edge. This is called a path. As you may have guessed, a path is an ordered sequence of vertices connected by edges. The length of a path is the number of edges in between. For example, if we have the path A, B, E, C, B, and D, the length of it will be 5. Connectivity is another term we need to know about graphs. Two vertices are connected if there's a path between them. Otherwise, they aren't connected. A connected graph has a path between any two vertices. On the other hand, a complete graph must make every pair of vertices connected by a unique edge. Here's what a connected graph looks like. As you can see, there's a path between any two vertices in the graph. But an unconnected graph, on the other hand, doesn't always have a path between every pair of vertices. The vertices with orange edges aren't connected to the rest of the graph. If we take a look at a complete graph, we can see that every vertex has a unique edge to everyone else. If you think of graphs as maps, each vertex represents a city, and edges are the roads connecting them. Because each road has different distances or speed limits, similarly in graphs, we can assign a weight value on each edge. And this graph becomes a weighted graph. Here we have a graph with each edge's weight next to them. Please note that the weight values are not necessarily visualized as the length of the edges. For example, in this graph, every edge appears to have the same length, but their weights are very different. So, how is the graph different from a tree? Trees are connected graphs that have a unique path between any pair of vertices. Or in other words, there are no circles. Here we have 3 trees which use the same vertices. As you can see, any vertex can be the root of the tree. In directed graphs, we have a few more terminologies though. In undirected graphs, we use the degree of a vertex to count its neighbors. But in directed graphs, there are two types of neighbors depending on the direction of the edge. So we have two types of degrees. The out degree of a vertex is how many vertices the current vertex is pointing to, while the in degree of a vertex is how many vertices are pointing to the current vertex. For example, the in degree of V1 is 0 since no vertices are pointing to it. But the out degree of V1 is 2 because it's pointing to V2 and V4. If a vertex has in degree equal to 0, we call this vertex a source, like a faucet in a bathtub where water flows out. On the other hand, if we check V2, its in degree is 3, but out degree is 0. If a vertex has out degree equal to 0, we call it a sink, like a drain in the bathtub where water flows to. If we want to combine a weighted graph and a directed graph, we get a weighted directed graph, which looks something like this. As we explained earlier in this lecture, weighted graphs have a value associated with each edge. But unlike weighted undirected graphs, the edge from Vj to Vk is different than the edge from Vk to Vj. So they don't need to have the same weight. In this example, there are two edges between V5 and V3, but they have different weight. This is also very common in real-world scenarios. For example, a highway has two directions, but the traffic conditions may be different. Thus, each direction may have a different weight. Okay, so now that we know some graph terminologies and some different kinds of graphs, the next question is, how do we represent it in computers? We have three ways to do this: with a binary relation list, an adjacency matrix, or an adjacency list. Let's start with the binary relation list implementation. So a binary relation list is just a container storing all the edges in the graph. For example, we can use E to store all the edges. The memory usage will be in the order of the size of E. If we want to determine if the vertex J is adjacent to the vertex K, it'll take the order of the size of E runtime, because we'll have to check each edge. And if we want to find all the neighbors of vertex J, it'll also be in the order of the size of E runtime. So if this implementation isn't efficient, we need a better way to implement a graph. Another way to implement a graph is with an adjacency matrix. If we only needed an unweighted graph, we could just have a matrix of Boolean values, as shown here. If we suppose n is how many vertices there are, we need to create an n by n matrix of Boolean values. Therefore, if vertex I and vertex j are adjacent, then we can set the matrix at I and j and the matrix at j and I to true. This means that the matrix will be symmetric. So if we wanted to store a weighted graph with an adjacency matrix, we first define an n by n matrix A, and if vertex I and j are adjacent with the weight W, then we can set A at I and j and A at j and I equal to W. As you can see, we store the weights in the graph rather than Boolean values. But this graph is undirected. If the graph was directed, though, then the matrix wouldn't necessarily be symmetric. In this case, only the weight 0.24 is symmetric. That's because the edge from vertex 4 to vertex 3 happens to have the same weight as the edge from vertex 3 to vertex 4. Another implementation for graphs is with an adjacency list. In adjacency lists, each vertex in the graph is associated with a list of its neighbors. So this is essentially a sparse matrix representation. If we use this implementation, the memory usage will be in the order of the number of vertices plus the number of edges. Once graphs are represented, the next question is how to traverse them. In the previous lectures, we've already talked about how to traverse trees. The same techniques can be used here too. We can choose the breadth first traversal using the queue or the depth first traversal using the stack. Let's start with the breadth first traversal. Here's how it works. We're first going to choose any vertex as the starting point in the graph, mark it as visited, and then push it onto a queue. Then while the queue isn't empty, we pop the front vertex. Let's say V. Then for each vertex adjacent to V that's not visited, we can mark it as visited and push it into the queue. Now let's see how this looks like with an actual graph. So here we have a graph with vertices A through I. We'll start by adding A to the queue. Now we need to pop A from the queue and push its adjacent vertices to the queue. In this case, they are B, C, and E. Please note they can be added in the queue in any order, but if we prefer, we can keep them in alphabetical order. Now we pop B and push its adjacent vertices in the queue. We only have one new vertex, which is D. C is the first item in the queue, so we pop C and push its adjacent vertex, F, into the queue. When we pop E, E has two unvisited neighbors, H and G, so we can push those to the queue. When we check D, though, D doesn't have any unvisited neighbors, so we can just pop it from the queue. F is next in the queue, so let's check that. F doesn't have any new adjacent vertices, so let's pop F and move on to G. When we check G, we get one new neighbor, I, so we can pop G and add I to the queue. Now we check H and it doesn't have any new neighbors, so we just pop it. The last item is I, so let's pop that from the queue. Now the queue is empty, so we can stop here. As we know, the difference between a breadth first traversal and a depth first traversal is just the choice of queue versus stack. Let's see how the depth first traversal works now. First, we choose a vertex as a starting point, mark it visited, and push it into a stack. Then while the stack isn't empty, we can look at the top vertex in the stack, and if there's another unvisited adjacent vertex, we can mark it visited, and then push it to the stack. Otherwise, if there's no unvisited adjacent vertices, we can pop the stack. Let's have that graph from before. We start at vertex A and add it to the stack. We have one unvisited neighbor, B, so we can add that to the stack too. Please note here that we may have also chosen C or E, but if we prefer to visit in alphabetical order, we will pick B first. Now, B has an unvisited neighbor, C. C, in turn, also has an unvisited neighbor D, so let's add that. But D doesn't have any unvisited neighbors, so we pop it from the stack and go back to C. We do have another unvisited neighbor, E. E has an unvisited neighbor, G, so we can also add G to the stack. We continue with I and add it to the stack. And now we have H, so we can add that to the stack. So the stack here has no size limitations, but we don't need more space in this example. We can pop out H, I, G, and E from the stack since they don't have any unvisited neighbors. But C still has one, which is F. So we can add F. When we pop out the rest of the vertices, the stack is empty. So that means our traversal is complete. So there's two ways to traverse the graph, and the result will be different. Even for each traversal, it can traverse in different orders, because as we discussed, it's flexible on which neighbor to visit first if there are multiple of them. So in summary, we talked about the terminologies of graphs, such as the degree of a vertex, paths, etc. We also talked about directed and undirected graphs, and weighted and unweighted graphs. Then we moved on to graph representations, such as with adjacency matrices, binary relation lists, and adjacency lists. At the end, we talked about two traversals of graphs, including the breadth-first traversal and depth-first traversal. Congratulations on making it to the end of the course. I hope you learned a lot from the past 15 lectures. More importantly, I hope you enjoyed this course and felt excited about computer science. This concludes the entire course. Thank you so much for joining this course. Have fun and happy coding. Bye-bye.